Welcome all of you. We will continue with our discussion on the analysis of the proton NMR spectra. In the last class, I discussed about the multiplicity pattern for the protons of the phenyl group which is present in the molecule. And I told you, depending upon the substitution, whether it is a mono substitution or symmetrically or asymmetrically disubstituted ortho, meta or para benzenes, for each of the protons we arrived at the multiplicity pattern, okay, depending upon where the substituent is there. For example, I am looking for one proton and it has a substitution which is asymmetrically disubstituted in the meta position for that, then I can look at it and say what are the couplings it experiences, whether it is ortho, meta or para, whether it experiences one ortho coupling or two ortho couplings or one meta coupling or two meta couplings. I can arrive at the multiplicity pattern. If both the ortho couplings or meta couplings which is experienced by this proton are identical, then we may get a multiplicity pattern like triplet, and another proton which can interact with this can give rise to what is called triplet of doublets. If there is no other, all the couplings are different, there is no way they are overlapping, then each proton can experience coupling with the remaining three protons. I am talking about disubstituted benzene groups, in which case you are going to get 8-length pattern, doublet of doublet of doublet. So, we arrived at that, and I took one or two examples of the molecule to how to analyze the multiplicity pattern. And also, depending upon the substituent present in the molecule in the benzene group, at which position of a proton you are looking at, whether it is ortho position, meta or para position, and type of substitution which is there, there is a table of values which can be which says what is the contribution of this substituent for that chemical shift position of a particular proton. For example, I take a proton A, there could be ortho substitution to the nitrogen, meta or para can also be nitro group or some other group. Pick up the value for that from the table. Take the base value as 7.28 as the benzene. Do the addition of that. It is always, it could be positive contribution or negative contribution, does not matter. Whatever the sign is there in the table, you take it. Simply do co-addition of all of them and get the value. That is a predicted value of the chemical shift for protons of the phenyl group. And I showed you with 2 or 3 examples. By and large, the predicted values agrees with the experimental values to a reasonable extent. As I said, nothing can beat the experiment. Prediction is prediction, experiment is experiment. So, experimental values are the real values, but you can say it is very close to predicted values. Use that as a starting parameter for the assignment. Based on that, after the assignment, go back and look at the multiplicity pattern. What is the multiplicity pattern we are going to see for each proton, like what I have already discussed, whether it agrees or not. And that is one easiest way to make the assignment of the protons of the phenyl group. Any type of phenyl group, depending upon whatever the substituent you have in whatever the position, we can make the assignment. Okay, with that we have fairly understood, lot of analysis we have done. We go further. So far we are looking only at the proton spectrum, where we are looking at the proton-proton couplings. The J couplings what we saw are only proton-proton. Can there be a heteronuclear coupling in proton? Can a heteronuclear couple to proton? Why not? It should couple. Then what will happen to the spectrum? How it gets reflected? How do we extract the heteronuclear coupling? We look at it now. Take for example a molecule like BH4, an ion. I am looking at the proton. There is a boron attached to it. Remember, boron has 2 isotopes, boron spin 3 and spin 3 by 2. Boron 10 is spin 3, boron 11 is spin 3 by 2. And each of them has a different abundance, and ratio is 1:4, abundance ratio 1:4. And boron will split this proton. I am looking at proton, but it is coupled to boron. And what is the multiplicity pattern you get? Simply let us put 2Ni+1 rule. Even for this, even though there is chemical equivalence, I am talking about only one boron. Put n is equal to 1, 2. Let us say spin for this. I take an example of boron 10. Spin is 3 plus 1. So, it should give 7 lines. For boron 10 should give 7 lines. Put for boron 11, then what will happen? 2 into 3 by 2 into 1 plus 1. So, it would give 4 lines. So, boron 11 should give 4 lines and boron 10 should give you 7 lines. But intensity ratio is 20:80. See, boron 10 intensity is small, it should give 7 lines of intensity, at least 1/4 of the bigger line. So, both the isotopes, both boron 10 and boron 11 individually they are coupled to proton. So, that means you have, if I take 100 molecules of BH4, 20 molecules are with spin B10, 10BH4 and 80 molecules are 11BH4. There are both the molecules present, both isotopomers are present. You understand? Both the isotopomers are present. As a consequence, you get the spectrum of, in this proton spectrum, coupling of both boron 10 and boron 11 will be present. It is the overlap spectrum of both molecules. So, one spectrum for boron 11 spin 3 by 2, 4 peaks are there of equal intensity. That is what we calculated. That is from boron 11 H4 molecule. And there is another 20% of the molecule will have boron 10 with spin 3, that gives us to 8 lines. And intensity ratio you see 1:4. And this separation gives me 11 boron proton coupling, this separation gives me 10 boron and proton coupling. You understand? When there are two different isotopomers, because of two different isotopes, then both of them can couple to the proton and the spectrum is the overlap of both the isotopomers. This is a classical example of BH4. I am looking at the proton NMR where B10 and B11 both are coupled. In the sense they are not in the same molecule. Please always remember there are two different types of molecules. Boron 10 H4 is one molecule, boron 11 H4 is another molecule. Their abundance ratio is different because of their abundance is 20:80 and coupling is different because spins are 3 and 3 by 2. As a consequence, the pattern is different. And measuring this separation gives you 11BH coupling, this separation gives me 10BH coupling. Okay, that is what it is. We got everything. So, we can easily understand all those things, coupling with this thing. Okay. We will go to the next molecule. There need not be one heteronuclei. Remember when I was explaining the spin-spin interactions, scalar coupling salient features, I said one spin can experience coupling with n number of other nuclei, NMR active nuclei simultaneously with different coupling strengths. So, if I consider CH3 proton, it can experience coupling with this CH2 proton with proton spin half. Of course, if I label it, it can couple with the carbon also. Since it is a natural abundance, we will not worry about it, it will be satellites. It can still sulfur, it does not will not couple. Phosphorus will couple, spin half. Fluorine will couple, spin half. And the extent of coupling depends upon how far they are separated, how many bonds they are separated. As a consequence, if I look at a simple molecule, I can find out multiplicity pattern depending upon the interactions. And of course, I am looking at the proton NMR. Then if I look at the proton NMR, there are only two groups which gives the proton signal. This is CH3. I can clearly say high field region is CH3 and low field region is CH2. No doubt about it. And why CH3 is a triplet? Because it is coupled to CH2. That is fine. But now look at this molecule. This also has coupling, can couple with phosphorus and fluorine. If you carefully see this molecule, you will see each line of the triplet. This triplet separation is HH coupling and each line of this triplet is further split into a triplet because of fluorine. See this separation, if you take this triplet here, this separation if you measure, it will give me JHF coupling. HF is for CH3 proton and this separation gives me HH coupling. Then you may ask me what will happen to phosphorus. Phosphorus is experiencing 1, 2, 3, 4 bond coupling, which may be very small. 4 bond proton phosphorus coupling may be very small. So, you are not seeing, whereas this one 5 bond coupling may be visible, you are seeing that. So, as a consequence, in this case of this molecule, what you are looking at is a CH3 proton. This CH3 proton is a triplet of a triplet and the first triplet is coming because of CH3 coupled to CH2 and each line of the triplet is split into another triplet because of F2, and phosphorus is not coupled to this. That is it. I can measure the separation. I know HH coupling between this and this is 7 hertz. I know 5 bond coupling is 0.7 hertz. We got triplet of triplet. Phosphorus is not coupled to that here. What about this one? Obviously, you can say this is a CH2 group, and CH2 group, this CH2 group will couple to this one. What is the pattern we expect? We expect that pattern to be a quartet. Further, what will happen? This CH2 is not far away for phosphorus and for fluorine. It couples to both of them. Then depending upon the strength of the coupling, let us say this coupling is larger, then each line of the quartet is going to be a triplet because of fluorine, and then it is going to be quartet of triplets. Further, what will happen? It is also split into each line of that into a doublet because of phosphorus. Depending upon which is larger, which strength is larger, whether it is triplet or quartet of triplet of doublet or quartet of doublet of triplet or triplet of doublet of quartet, we do not know. That depends upon the strength of the coupling, that you can measure it. We will start like this for this molecule. Let us say that is the chemical shift. It is always at the center of the multiplicity. I told you that is CH2 proton, that initially splits into a doublet because of phosphorus coupling, because that means that coupling is larger. That is how I have worked out the multiplicity pattern here. Then it also has a coupling to this. This is second largest coupling. First largest coupling I took to be HP, that is very large, and each line of the doublet is becoming a quartet because of coupling with CH3 protons. This is one quartet, another quartet. I have deliberately put two different colors. Now what will happen? It is also coupled to fluorine. Here fluorine is far away. So in this case phosphorus was far away, is not coupled, but here phosphorus is also coupled, fluorine is also coupled, and fluorine is equivalent to fluorines. So it will make each line of this into doublet of quartet. Quartets of doublet was there, or this coupling if you take larger, it is doublet of quartets, and each line of these two quartets will be a triplet because of two fluorines, equivalent fluorine. You get like this. It is doublet of quartets of a triplet. This is the pattern you are going to get. Simple molecule. Okay, I am looking at the proton NMR, but still I am able to get the couplings. I am able to measure coupling of heteronuclear couplings in this. So heteronuclear couplings are reflected in the spectrum. Now I will ask you one question in this molecule. What about PF coupling? Why we are not seeing here and here? You must remember, I told you this is a passive coupling. You are looking at proton. Proton can give rise to coupling to phosphorus and fluorine, whereas phosphorus and fluorine are passive spins. Passive spin coupling is not reflected at the site of the active spin. Now both the protons we are looking are active spins, and Pa and F are passive spins. Their couplings are not seen here. You understand this? That is there. PF coupling is there, but not seen here. Okay. Go to the next molecule. This is a simple molecule where one fluorine is present and there are three protons. I can start making the assignment very easily. There are three groups of protons here. Fairly easy to analyze if you look at it. This is a broad triplet with a separation quite large here, a triplet. What this could be? I would say this proton has a two ortho coupling with proton and fluorine. By the way, mind you, ortho coupling in the benzene with the proton and fluorine is similar values that of the proton. Ortho coupling between proton if it is in the benzene is 8 hertz, fluorine is also around 78 hertz. Generally they have similar strength. So this coupling and this coupling are identical, and I would say this triplet corresponds to proton 1. That is my assumption. Then what about the next one? Next one is proton 2. What are the possible couplings we can think of for the proton 2? If this is proton 2, you can have one ortho coupling and two meta couplings. And if both the meta couplings are different, then it is going to be 8 line pattern. Large separation is because of this ortho, and each line is split into 8 lines like this. It is going to be doublet of doublets. So, this could be proton 2, my assumption. Then what is the last one? This is proton 3. Proton 3 has two meta couplings and they are different. 2,3 coupling and fluorine proton, this fluorine proton couplings are different. So, it is doublet of doublet. Very easily you can start interpreting all those things. Okay. So, this is 3, what I said is correct, this is 2, this is 1, perfect. Very easily we can interpret these things. So, this is doublet of doublet, this is doublet of doublet of doublet, this is also doublet of doublet. In principle, it is triplet, 2 lines are overlapped. So, very easily we can get the HF coupling here. In the earlier case, PF coupling and HF coupling both were there, here HF couplings are there. Now, take an example of a molecule like this, a very simple molecule. Now, we can expect 2 bond and 3 bond proton fluorine coupling here, because this proton phosphorus coupling, phosphorus here it can couple with CH2, it can also couple with CH3. And there is phenyl groups are there, forget about it, they are overlapped here. Very, of course, there also proton might have 2 bond 3 bond couplings, very fairly difficult to extract there. I am not analyzing that region, we are analyzing only this region. That region means coupling of phosphorus to CH3 protons and CH2 protons are the only two things we can think of now. If I think of that, I know this is CH3, I know this is CH2. This CH3 is going to be a triplet because of CH2, that is well known, HH coupling. And each line of the triplet is further split into doublet because of coupling with this phosphorus. Look at it, this is what it is. See, okay, this is CH3, we will come to that. Okay, we will also analyze CH2. CH2 is going to be a quartet because of this, fine. And each line of the quartet is a doublet because of phosphorus coupling. So, it will be depending upon which coupling is larger, it is doublet of quartet, similarly it is doublet of triplets. Look at this one, this is one quartet, another quartet, and this separation here gives me HP coupling, coupling between phosphorus and proton, and this separation is going to give you HH coupling, is a quartet. There are 2 quartets, very easily you can identify. Similarly, here this one triplet because of coupling of CH3 with CH2, the another triplet, and this separation of the each of these identical lines you can consider leftmost to leftmost, right to right, or center to center. Measure the separation, that will give you HH coupling. Exactly what you got here, here also you will get HH coupling. And interesting thing what you notice here is, see here, very interesting thing I want to tell you, the 3 bond proton coupling is 16 Hertz, whereas 2 bond proton coupling is about 10 points, proton phosphorus coupling is 10 Hertz. Usually what we say, as the number of bonds keep increasing, consecutive bonds, coupling strength decreases. But you see, you can also see strange things here. 3 bond phosphorus proton coupling is larger than 2 bond phosphorus proton coupling. Strange things do happen in NMR, please remember. Okay, this is what it is. We could make the analysis of this thing very easily. We will go further now. Another molecule I am going to take. This is a very interesting molecule. I am not worried about the phenyl group. I am concentrating only on these 3 protons and coupled to phosphorus. I am looking only at the proton NMR. And these 3 regions are there, correspond to 3 protons, 1, 2 and 3. And you can easily understand, if I consider this phosphorus, this proton, it can have a geminal coupling with phosphorus, trans with this and cis with this. Similarly, consider this one, this can have a geminal with this, trans with this and cis with this. Consider this proton, this can have geminal with this, cis with this and trans with this. Each of these proton experiences 3 different types of coupling, including one of them is a phosphorus. So, very easily you can interpret depending upon the strength of our trans coupling. Of course, we know trans coupling is larger than cis, then geminal. Same this thing follows here also. I would say this is proton 3. For the reason, I would say trans coupling of proton is larger than cis coupling of phosphorus and proton, which is about 14 Hertz, and then geminal coupling of proton is very small. This is geminal coupling is usually 1 to 2 Hertz I told you, or maybe 3 Hertz. So, very easily you can see this is going to be a broad first doublet, and each line of this doublet is further split into lengths, and then they will further split because of geminal coupling. It is 8 line pattern DDD, correct. What is the next one? Next one I would say this is proton 2. Why did I say that? Remember, the trans coupling is larger and the trans coupling with phosphorus proton is huge, of the order of 32 hertz, quite large. So, there is a large separation here into a doublet, and each length of the doublet is split because of the cis coupling into 2 doublets, and further each is split into a doublet because of geminal coupling. This is a 8 line pattern. Go to the next one. Obviously, this is proton 1. Proton 1 has one trans coupling, cis coupling, and also geminal with proton. See, geminal with proton is geminal with phosphorus is 12 hertz, trans is 18, this is 11.4. We know that. You start writing down, this is the pattern you are going to get. Large coupling with trans with proton, then geminal with phosphorus, and then cis with proton. So, it is going to be 8 line pattern. There are 8 lanes there, if you carefully see, some are overlapped here. So, this is the DDD pattern. So, very easily you can understand. We will go further and we see the coupling with fluorine. This is a simple molecule called 3-fluoropropanol. We should get proton fluorine couplings here. Why I am taking proton, phosphorus, etc.? There are abundant spins. If there are less abundant spins, you do not get like this, you get like satellites. I will come to that later. In this molecule, if you expand this, it is going to be doublet of triplet of triplet. If you expand this, it is a triplet. This is again doublet of triplet. Why it is like that? I can say this is triplet. Where is the triplet coming from? This one. This proton is a triplet. Why it is a triplet? Because it is coupled to CH2. And what about this one? This is going to be triplet because of this, triplet of a triplet because of this, and it also has a coupling with fluorine. This one is a triplet because of this and also doublet because of this. Very easily we will start explaining the multiplicity pattern based on the coupling strengths. Look at this, this is, I will say this is proton 3. Proton 3 is a triplet because of this large coupling, and then there is a one bond coupling with fluorine, FH coupling, that is quite large, that is doublet 45 hertz, and then it is going to be a first day doublet. Each line of the doublet is split into a triplet like this. That is why I would fairly say this is proton 3. Then I would say proton 2. Proton 2 again is a pentet, you know, like you I told you already, when we have two proton CH2 groups coupled to one CH2 group or one CH, we get a quintet like pattern like this, 5 line pattern 1 4 6 4 1, and that is split into a doublet because of coupling fluorine, which is about 24 hertz. That is why it appears as doublet of, actually it is a quintet, it appears like triplet of triplet because two triplets are there overlapped. This is experiencing triplet because of this and triplet because of this. If triplet of a triplet is overlapped unresolved, it looks like a quintet. So, it is doublet of triplet of triplet, that is also correct. Then obviously leftover is proton 1. What is it proton 1? This proton 1, it does not experience a fluorine coupling, very small, it experiences only coupling with the CH2 and is a triplet. Very easily you can interpret this one and get the proton fluorine couplings in this molecule. Look at this one, this is a very simple molecule with a phosphorus coupling, and we have only one group of CH2s here, but there are two types of phosphorus here. One has a small coupling, other has a large coupling. So, if you all these three protons, they are chemically equivalent, you take it one line you get, and it will split into a doublet because of this phosphorus and splits into another doublet because of other phosphorus, and you get 4 line pattern of equal intensity. It is a fantastic example of weakly coupled spin. You see, all the lengths are of equal intensity because they are heteronuclei. I always said, earlier I said, remember this, heteronuclear spin system are always weakly coupled. Okay. With this you have got some idea about how do we extract the coupling, heteronuclear coupling from the proton spectrum. So far I was considering only abundant spins. What happens when you have a less abundant spins like carbon 13, nitrogen 15, silicon, selenium, like that? How do we get the spectrum? We look at it now. Before that, I go into the isotopomers, which you already most of you know. I will tell you again. Consider CHCl3, 100 molecules. Well, there is 1 carbon, 1 proton, 3 chlorines. We will not worry about chlorine isotopes. We will consider only carbon. Carbon has 2 isotopes. Forget about carbon 14. This is 99% abundant. This is 1.1%. 1% you take it. So, if I have 100 molecule, 99 molecules are carbon 12 and 1 molecule is carbon 13. That means this carbon 12 will not give the signal at all. Only proton will give, carbon 2 will not give the signal. Whereas this here, proton will give signal, but it also couples with this carbon. Even though it is 1% abundant, it spin half nuclei. Carbon 12 is spin 0, carbon 13 is spin half, it can couple to that and give rise to splitting. And this 1 molecule here is NMR active, 99 molecules here are especially in NMR inactive as far as carbon is concerned, not for proton. So, intensity of the certain acetylates now when it is coupled to proton, if I have 1% molecule if I consider, I say proton signal is 99%. 99% of the signal comes from carbon 12 attached proton, because that carbon 12 will not couple, you get a single peak. But 1% of the molecule is there, that will couple to proton and splits into a doublet, and this intensity is only 1%, and 1% of the intensity on either side further split into 2, it will become 0.5 here and 0.5 here. These are all very small compared to these big peaks. That is why they are called satellites. Satellite peaks are seen when an abundant spin is coupled to low abundant spin like nitrogen 15, silicon, mercury, etc. You will see the example of that. I hope you understood. When you have abundant spin coupled to rare spin splitting is seen as a small weak peaks on either side of the coupled main peak, and they are called satellites. If you analyze the satellite spectrum, you will get the coupling between proton and the satellites. Okay, as a coupled spin as which gives signal as satellite. Take for example CHCl3, that is what I explained to you. 99% of the molecule is coming are present, and the main signal of proton comes because of this C12 attached, which will not split to this proton, it gives only single peak. Intensity is very high, but 1% of the molecule will split because of carbon 13. So, the proton will become a doublet, and this doublet separation, what does it give you then? It will give you JCH, coupling between carbon and proton. Already 1% abundant, further split into 2. So, it will become 0.5% intensity, 0.5% here compared to the main peak, and very small peaks. Sometimes you will not see it unless you enhance the signal very high. Vertically you have to enhance the signal, then only you will see. That is why these are called satellite peaks, satellites. Okay? And this separation gives me 1 bond carbon proton coupling. You understood? Less abundant spin can also couple to abundant spin, and you get the coupling from the satellite pattern. Same example, let us look at the TMS. TMS, if I look at the proton spectrum, major signal comes because of this proton, and there is also silicon. Silicon has an abundance of about 4.7%, and that gives rise to, of course, coupling here, and that is because of coupled to carbon 1%, and is also having silicon 4% and coupled here. You can see 2 peaks here. These 2 peaks are because of silicon proton coupling. See, this is because of carbon proton coupling, this is because of silicon proton coupling. There are 2 less abundant spins here, silicon and carbon. Both of them can couple to proton. This is a 1 bond carbon proton coupling, this is a 2 bond silicon proton coupling. So, 1 bond carbon proton coupling you can get as nearly 119 hertz, whereas this is 2 bond 6.6 hertz. You got everything. Very easily you can measure coupling between less abundant spin and abundant spin from the satellite spectrum. Okay. We will look for another molecule SiHCl3. It is a simple molecule. Look at the proton NMR is huge, and it is coupled to silicon, there is no carbon here. Then this separation gives me 1 bond silicon proton coupling is huge, is of the order of 366 hertz. You can see 1 bond silicon proton coupling we could get from the satellite spectrum of this molecule. Let us look at this molecule. It is a fairly simple molecule, but the spectrum is very interesting. If you look at the 100 megahertz spectrum of this molecule, there are 3 groups of protons. This is iodine, this is selenium. Selenium is also less abundant. Even it couples to these 3 protons, this also gives rise to satellites. First you have to make the assignment for the proton peaks. First I make the assignment for the proton peak like this 1, 2 and 3 by using the splitting idea of my splitting pattern, which I already discussed several times. I will say this is the proton 1 which has a large ortho coupling, then meta coupling, so it is like this. Then 2 is both of them are nearly equal coupling, you get like this, and 3 is very small, both very weak couplings. As a consequence, I would based on the splitting separation of the multiplicity pattern of the coupled peaks, coupled spins peaks separation, I would say this is proton 3, this is proton 2 and proton 1. That is fine, that assignment is good. But carefully if you see, something interesting is you are going to see what are these lines coming, they are exactly matching with this, these lines matching with this separation, they are the satellites. This silicon can couple to this proton, 2 bond coupling is there, and this is okay coupling strength I have written, this is 2 bond proton selenium coupling, this is another side. So, this 3 proton can couple to selenium, and each of these lines is split into 2 peaks on either side you get, they are satellites, and measuring of the center of this to center of this peak will give you proton selenium coupling, you understand. So, here from that is what I said, this gives you proton selenium coupling and this also gives, because satellites you already saw in the previous example comes on either side. Similarly, if you go to this proton, this also has 46 hertz coupling, this proton 2 from center you have some peaks here which are overlapped, and from this one you see 4 peaks here, separation exactly like this. So, satellites are there for this group also, one is here, other is overlapped. For this one satellite is here, other are here, you see hidden. Go to this proton 1, this also has a long range coupling 1, 2 and 3, 3 bond selenium proton coupling, and you can see that is separated and it is about 8 hertz. This is one coupling, see one satellite for this one, and for this also you have 2 peaks on either side. Exactly similar pattern of the main peak you see on the other side as chota peaks like this, small peaks, they are called satellites. So, from this satellite I can get the selenium proton couplings also in this molecule, very easily we can understand this. So, I gave an example today about how we can analyze the proton spectrum in this class about heteronuclear coupling. So far we were analyzing homonuclear spectrum. Now I showed you how we can get heteronuclear coupling. Proton can couple to abundant species like phosphorus, fluorine, and I showed many examples how we can extract phosphorus coupling, fluorine coupling. Simultaneously proton and fluorine both can be present. You can have simultaneous coupling of both heteronuclei, both can be extracted. We took the example of a molecule where proton is experiencing coupling with phosphorus and also with fluorine. Other examples, proton is experiencing coupling only with phosphorus and only with fluorine, all examples we saw. There are abundant spins. There are examples it can couple to, proton can couple to less abundant spins like carbon, nitrogen, tin, etc. Selenium, silicon, we saw some examples. They are all abundant spins, they give rise to satellites because the major abundance portion is different and they will not have spin and they will not generally couple to this. And then only the other one, like for example carbon 13, carbon 12 spin is 0, that will not couple, whereas carbon 13 will couple, give rise to satellites on either side, small peaks. Like this we can get the satellite spectrum, measure the separation which will be an equidistance from the center, you get this coupling between the protons and the dilute spin. Like this we can analyze the spectrum and get the heteronuclear coupling between abundant spin and the rare spin or the dilute spin. So, I will stop here, we will continue further in the next class. Thank you.